Okay, so what we have done is we have first seen what is a PN junction diode. What do you mean by PN junction diode? So here we have seen P type of material which is doped by using trivalent impurities, and it has majority charge carriers as hole and minority charge carriers as electrons. On another side, we have seen N type material which is doped with pentavalent impurities. So majority charge carriers are electrons and minority charge carriers are holes, due to which we have seen a formation of depletion region. So when you connect them together at this particular point, at the junction of this, you are going to get a depletion region. And we have seen that the depletion region will not allow further movement of electrons and holes in between this particular wafer. So in order to do so, you need to apply additional electric field. So we have seen that we connect this particular battery. This battery is connected in two different ways. One of the way is shown in front of you over here. So first we connect this battery in such a manner that the anode is positive and the cathode is negative. This is termed as forward bias, and the diode will conduct after 0.7 volt if it is made up of silicon material. If you connect this battery as shown in figure, that is positive towards the cathode and negative towards the anode, we have seen that this particular is known as reverse bias, and the width of this depletion region, the width will increase and there will not be any current flow through the diode under a normal potential. You go on increasing the potential and somewhere at the range of 20, 25, 30, the diode will conduct and current will flow through the circuit. So drawing the characteristics of the diode, we have seen this as the characteristics of a diode. So we have seen that when you configure the diode into the forward bias, what will happen is if you apply just 0.7 volt also, then also what will happen is if you just apply 0.7 volt also, then also the diode will start conducting. So here is a graph that we have seen that at 0.7 volt the diode will conduct, and during reverse bias, if you go for the reverse bias, then whatever voltage you apply, the diode will not conduct up to a large amount of voltage, and after the peak inverse voltage, which is somewhere in the range of 20, 30, 40, depending upon the manufacturing of the diode will conduct. So one common conclusion we had obtained in this particular circuit is that the diode will conduct during the forward bias and the diode will not conduct during the reverse bias. This is a common conclusion we had during our first lecture. Then we had seen how to do the experimental setup to obtain the reverse and forward characteristics of the diode. So here we have seen that you connect the circuit as shown into figure, then you go on increasing the voltage during the forward bias. You will find that up to 0.7 there will not be any current. Then after 0.7 the diode will start conducting, the voltage across diode remain constant during the forward bias, and during the reverse bias you are going to obtain zero current forever. So this is the setup that we have seen to plot the characteristics, and when you plot the characteristics you are going to get the graph as shown over here into the figure. So these are the things we have seen regarding to the diode. Now what was the reason to see these things was to find out what are the uses of this particular technique. So in our next diagram we have seen a rectifier, which is called as a half wave rectifier. So here there is a circuit drawn which is known as a half wave rectifier. So you can see here there is a half wave rectifier. What is a simple circuit? We have seen that when you have a half wave rectifier, then you have a normal step down transformer. So I will just repeat, this is what a step down transformer, where you can see that blue line. This is a step down transformer. As drawn in a figure, you can find the step down transformer will convert AC supply 230 volt to 50 hertz supply. Now for an example, I have written 12 volt over here. It is not that it will be always 12 volt. It is not like that it will be always 12 volt. So as an example, I have written 12 volt over there. It can be 8, 12, 14, 20, 25 depending upon your requirements. Then we have seen it has two cycles. One is positive half cycle, another is negative half cycle. So at this particular point, you can see in a diagram that we have a positive half cycle there. During positive half cycle, terminal A becomes positive, B becomes negative. Diode becomes forward bias and diode will start conducting. Since the diode is conducting, you can find there is an output voltage which is available over here. There is an output voltage which is available over here because the diode is under conduction. So we can say that during positive half cycle, A becomes positive, B becomes negative, and the diode becomes forward bias. The diode will conduct and output voltage is available. Now, what will happen during negative half cycle that you can see in this negative half cycle? So during negative half cycle, what will happen? At the top of this negative half cycle, we have written that terminal B will be positive with respect to terminal A, and the diode will become reverse bias. As soon as the diode becomes reverse bias, there is no current through the circuit, and as you can see over here in the output cycle, since there is no current inside the circuit, the output will become 0. So when the output becomes 0, you can find that from the load terminal during positive half cycle there is a current flow. So we can see as shown over here, the current will always flow from terminal X to Y, and I can say that the AC waveform has been converted into a DC waveform. This was a very simple logic that we have discussed regarding to the half wave rectifier. Now what happens to this particular circuit when you are talking about half wave rectifier, that we have tried to understood over here, that what are the disadvantages of half wave rectifier. But before that, how you perform the analysis of a rectifier or a circuit, that let us see over here. There are two factors which you have to deal with as shown over here. The first factor is regarding to the what is the this ripple factor of the circuit. So ripple factor, you can find out RMS value of AC upon the DC value of the component, that is Vrms upon Vdc. By solving this, we have reached towards this particular conclusion, that what is the formula for the ripple factor. As shown in that particular formula, ripple can be given as root of Vrms upon Vdc bracket square minus 1. In order to solve this, you need to find out these two parameters. Which two parameters? That have been shown in front of you. One is Vrms and another is V average. So question is, sir, वो VDC भी बोलता है उधर और इधर VRMS बोलता है. Oh, it's one and the same thing. VDC is nothing but V average. So one thing is clear, we need to find out these two parameters, that is V average and VRMS. So let us go through the waveform of half wave rectifier. You can see here in this waveform of half wave rectifier, which has been drawn in front of you. So in this half wave rectifier, we can find out that the output is available from 0 to pi, and the time period of the waveform is from 0 to 2 pi. So what will happen is, you can see here what I have written. I have written that the time period of the waveform is from 0 to 2 pi, and we can see that the waveform is only available up to this particular time period, that is 0 to pi. Over here you can see in the waveform. So it is only available up to 0 from 0 to pi. So the equation for this particular waveform can be given as, V average can be given 1 upon 2 pi integration from 0 to pi Vm sin theta d theta. So now why this happens, that you need to understand. When you are calculating a time period of this waveform, you can see this red color dot. The time period of the waveform is from 0 to 2 pi. But the waveform is actually available in between a time period of 0 to pi. So that is the reason when you write down the equation, of V average, what you do is, so you say that it is 1 upon 2 pi integration from 0 to pi Vm sin theta. Now the question is, why you are saying it up to integration from 0 to pi is the reason for which is the waveform is available only from the portion 0 to pi. From pi to 2 pi, the value of waveform is going to become 0. You can see where the red dot is moving. So it is only available from 0 to pi, and from pi to 2 pi the waveform is having 0 value, and due to which you have to write down the equation as shown in the calculation of average, 1 upon 2 pi integration from 0 to pi Vm sin theta d theta. ये इतना इसका लॉजिक जो है वो सिंपल है. इसको सॉल्व करेंगे हम लोग. Vm becoming constant will come outside. See this portion. You solve this particular equation and then you will get, you are going to get Vm upon 2 pi integration of sin theta. Now sin theta का integration minus cos theta, minus को बाहर निकालो. So let us come over here. माइनस को बाहर निकालो, so you are going to get minus of Vm upon 2 pi. Integration solve करो, cos I minus cos of 0. So this becomes Vm upon pi. So you found value of V average, that is nothing but VDC. Once you found value of VDC, let us start with the RMS value. So RMS value also, here the calculations are made. So what are the calculations? VRMS square is equal to 1 upon 2 pi integration 0 to pi Vm square sine square theta. So you solve this sine square, integration cannot be taken as shown over here, 1 minus cos of 2 theta upon 2. Then by solving this equation, you are going to get value of VRMS. We have found value of VRMS. VRMS can be given by Vm upon 2. So this was our final conclusion, that VRMS can be given by Vm upon 2 and V average, that is VDC, can be given as Vm upon pi. For a half-wave rectifier, we are talking about half-wave rectifier. Half-wave rectifier means the waveforms which are available over here in front of you. So we are talking about a half-wave rectifier. And then let us calculate the ripple factor. So we have done some simple calculations to calculate the ripple factor. The efficiency of the efficiency of your circuit and the TUF of the transformer. So we have done some very simple calculations and we found that the ripple factor is 1.21. The efficiency can be given as 40.6% and the TUF is obtained 0.287. So after this, let us quickly go to our next circuit. So what are the limitations of half-wave rectifier that you have seen? The first limitation is you can see the output is only available for the 50% of the time. So for 50% of the time as shown over here, for 50% of the time as shown over here in the figure, as 50% of the time the output is not available. Please see the two lines what I have drawn there. So for the 50% of the time the output is not available. That is first problem. So what we have seen is regarding to the efficiency. Efficiency, you have seen when we calculated the efficiency, it is somewhere around to the 40%. Now, in order to solve this problem, we had gone through two different solutions. So we are going to obtain a full wave rectifier. Here you can see that full wave rectifier has two types. One is center tap full wave rectifier, which consists of two diodes, diode D1 and diode D2. And the second is bridge wave rectifier, which consists of four diodes, diode D1, D2, D3 and D4. So let us quickly see one by one how they function. I will just quickly explain you how this center tap rectifier and these things are functioning. So first diagram we have seen was regarding to the center tap transformer rectifier. So what is the basic function of center tap transformer is, what is the basic benefit of using center tap transformer is you will find that the secondary winding, here is a step down transformer which is on the secondary side. The secondary winding is tapped at the center. So when you get the output voltage is such that during positive half cycle, as I have shown over here. So the benefit of this circuit is that you can see here, the during positive half cycle, X is greater than Y is greater than Z. So diode D1 becomes forward bias, diode D2 becomes reverse bias. During negative half cycle as shown over here, Z is positive with respect to Y is positive with respect to X. So diode D2 becomes forward bias, diode D1 becomes reverse bias. So one thing is clear, during positive half cycle, diode D1 will function. During negative half cycle, diode D2 will function. So let us understand the operation by using the waveform. So here I am going to see that there is a positive cycle. So during positive cycle, you can see here X is positive with respect to Y is positive with respect to Z. Diode D1 will become on, and you can see in the output in the output side as shown in this particular figure. In the output side, you will find diode D1 becomes on, diode D2 becomes off, and you are going to get the output. The current will flow. The flow of current has also been indicated in this diagram. The current will start from point X. The current will flow from point X to D1 to point W to RL to point Y. So this is how the direction of current will be, and the current will flow like this. Diode D2 will remain off. So you are going to get positive half cycle across the load resistor RL. Now talking about the negative half cycle, you can see over here that during negative half cycle, what will happen is Z will become positive with respect to Y will become positive with respect to X. and your diode D2 will conduct, D1 will remain off. So when your diode D2 will conduct, how the current will flow? Please see into the circuit diagram. The current will start from point Z to D2. That is the first point, how the current will flow from Z to D2. Then the current will travel to W to RL. So this is how the current will travel through W to RL, and then it will reach to terminal Y as shown in figure. So now in this manner you can see that during negative half cycle the current flows from entirely different part, that is Z, D to W, RL and Y. So in this manner we can see that during the negative half cycle also the current through load will flow from W to Y only, and see in the waveform which we have drawn as shown in figure, you can see the current will flow from point Z to D2 to W to get the positive half cycle. So in this manner, by using center tap transformer also, you are going to get the positive half cycle. Positive half cycle in both the cases. So the first disadvantage of your of your half wave rectifier has been removed, that now you are going to get output waveforms for both the cycles, positive as well as negative. Now, what was the problem regarding to the center tap rectifier? We have seen the secondary winding is tapped at the center. What happens is, the first point is the center tap transformer as shown over here becomes bulky. The center tap transformer becomes bulky. Now, the center tap transformer becomes bulky and it also becomes costly. So that is the first problem. And second problem is that the diode which has been reused, this diode needs to have a PIV rating of 2 VM. That is the second problem. That you cannot have a diode with a normal PIV rating, that it needs to have 2 VM PIV rating. So it becomes costly. Now the problem is very clear over here, that you have a center tap transformer which is also costly and bulky, and diode required are also of 2 VM rating. So they are also costly diodes. And why they require 2 VM rating, that has been explained over here. If you remember, we had seen what is if you consider value of VM is equal to 5 volt. If you remember, we had discussed this thing, that if you consider value of VM is equal to 5 volt, then what happens over here? You have upper winding voltage 5 volt, lower winding voltage 5 volt. So the diode which is off, that particular diode has to handle 10 volt even during the reverse bias. So we understood that the center tap transformer and the center tap half full wave rectifier is a beautiful rectifier, but along with two disadvantages. And when it comes to high cost, a human mind automatically start finding out the alternate solution. So what is the alternate solution that we have found? And that is bridge wave full wave rectifier. So you can see over here we have found a solution, that bridge wave full wave rectifier. So now let us go through the bridge wave full wave rectifier. So what they have done, instead of using a normal transformer, instead of using a standard tap transformer, here they had used a normal transformer now. So when they have used a normal transformer, now what is the benefit? The transformer is not bulky and the transformer is not costly also. So let us see what happens during the positive and negative half cycle. First 2 points are that during the positive half cycle, see over here, point X is positive with respect to point Y. And during negative half cycle, in the same waveform, you can see that where you have to see, I will show you here. See, this point Y is positive with respect to point X. You can see here point Y is positive with respect to point X. So let us quickly go through what happens in the circuit during the positive and negative half cycle. So one thing is clear, during the positive half cycle, for terminal X will become positive and terminal Y will become negative. So let me mark the positive terminal with this pink color. So what will happen is, this particular line will become positive, and let me mark the negative with yellow color. So what will happen is, this particular line Y will become negative. I hope you are able to see the positive and negative cycles there. The positive line is from X to W and the negative line is from Y to Z. So what will happen, you see that the positive line which is available there, in this positive line, it is connected to diode D1, and the negative line is connected to diode D3. I am talking about anode and cathode. The positive line is connected to anode of diode D1 and the negative is connected to cathode of diode D2, cathode of diode D3. So diode D1 and D3 will conduct, and diode D2 and D4 will not conduct. What I mean to say is, diode D1 and D3 will become forward bias and diode D2 and D4 will become reverse bias. So now diode D1 and D3 will conduct. So let us see how the current will flow. when diode D1 and D3 are under conduction, the current will start from point X to W. That is the first travel of current. Point X to W. Then at W, you can see diode D1 is conducting. So current will flow from point W to diode D1 to terminal A, as shown in figure. Point W to diode D1 to terminal A. Now at terminal A, you can see that diode D2 is under reverse bias. So current will take a path and current will travel from point A to RL to point B. In this manner, the current will travel from point A to RL to point B. In this manner, the current will travel. So now, once it reaches to point B, you can see diode D4 is reverse bias and diode D3 is forward bias. So current will travel from point B to diode D3 to terminal Z. And once it reaches to terminal Z, it will diode D2 in reverse bias. So the current will now end at point Y. So you can see here during positive half cycle, we can very clearly see that the current is flowing from point X to D1 to A to RL to B to Y. So this has been also indicated over here during positive half cycle. You can see, if you see in the waveform, that how the current will flow from X, W, D1, A, RL, B, D3, Z and Y. So now let us start with during negative half cycle. So as we can see over here, during negative half cycle, what happens is, you can see that point Y becomes positive with respect to point X. As you can see in the waveform where I have written there, that point Y becomes positive with respect to point X. So what will happen, this particular line, point Y to Z, it is going to become a positive line. Point X to W, this is going to become a negative line. So due to which D1 and D3 will become reverse bias and D2 and D4 will become forward bias. This has been indicated over here. If you see the waveform, diode D2 and D4 will become on and diode D1 and D3 will become off. Due to which how the current will flow, let us say Y is positive. So the first current will start from point Y to Z. Just see over here. The current has started from point Y and it has reached to point Z. So the current will start from point Y and it will reach to point Z. After that, when the current comes at point Z, it has two diodes in front of it, out of which D2 is forward bias and D3 is reverse bias. So current will flow from Z to D2 to point A. So you can see how the current travels. The current will travel from Z, D2 to point A. Once it reaches to point A, now you know that diode D1 is reverse bias. So current will enter through load resistance RL and it will reach at point B. So as shown in figure, it will once again come from point A to point B. Then obviously diode D4 is once again a forward bias diode. So it will go to diode D4 to point W. Once it reaches to point W, now diode D1 is reverse bias. So it will go to point X. So this is how the current will flow from point Y to point X. Now, if you see both these cycles, the direction of current through the load resistor RL will always remain same. And if I say during positive half cycle and during negative half cycle, I can very clearly see that the current will start at point A and it will flow to point B. So the current will always flow from point A to point B. And that is the reason the direction of current flowing through load resistor RL will always remain same, and we say that the AC waveform has been converted into DC waveform. So this is how we have seen the full wave bridge wave rectifier. In case of the full wave bridge wave rectifier also, you are going to get the cycle as shown in figure. In order to see the mathematical analysis of this full wave rectifier, we need to go towards our last lecture's derivation, and we have to see how this full wave rectifier works. So we can see over here, the time period will become 0 to pi. The time period of this waveform will become 0 to pi, because after pi this waveform will start repeating. And the waveform is do not have two segments, it is a single segment from 0 to pi. So the time period has been written 0 to pi, and the equation has been written V of theta is equal to Vm sin theta. You can concentrate to that color, highlighter color which I am using. Now let us write down the average and RMS equation. So we know that V average is equal to 1 upon pi integration from 0 to pi Vm sin theta. Once you solve it, you are going to get an equation, you are going to get an answer of V average. V average is nothing but VDC I am talking about. So you are going to get a average value of V average is equal to 2 Vm upon pi. You need to find out RMS value. Once again, the same idea for finding out the RMS value. Vrms square is equal to 1 upon pi integration from 0 to pi Vm square sine square theta. So now we know all of us know that the sine square theta cannot be solved. So we are taking that is 1 minus cos of 2 theta upon 2 as shown in this particular equation. So after solving this, you are going to get the value of RMS, that is Vrms. So Vrms can be given as Vm upon root 2 as shown in this equation. So we found Vrms is equal to Vm upon root 2. Once we solve this, now you have average value and RMS value in your hand, that is DC value and RMS value. Just put them into the equation and you can find out what is the value of ripple factor. So here I will find out value of ripple factor. So we can see here that the value of ripple factor is 0.482. So in this manner, if we compare this 0.482 value of ripple factor uh, with the previous ripple factor that we have got for the half wave rectifier, I will show you where the half wave rectifier ripple factor was. So here you can see the value of ripple factor was 1.21. So if you compare this, then you are going to understand that the value of ripple factor is improved to a larger extent because you are going to get the output in both the sectors. And similarly, you do for calculations for the efficiency and you find that the value of efficiency is somewhere around 81.20%. So in this manner, we have seen the comparison between the half wave rectifier and the full wave rectifier. We have seen how this half wave and full wave rectifier works. We have seen their mathematical analysis and many things. So what is next? The next is you are performing this ripple factor calculation, and you can see here how you do the ripple factor calculation is just a minute. Your ripple factor calculation, how they are done. So you calculate the RMS value of AC upon the DC component value in the output voltage. What does it mean? This variation of this particular signal, if you see here, then if you see in this case, the variation of the signal, if I ask you how much is the variation of the signal, then you can find your signal starts varying at 0.0, it reaches to 0.Vm, and once again it comes back to 0. So what is the variation in the signal? The variation in the signal is from 0 to Vm. So now we have to avoid this if you want to improve the value of ripple factor. In order to avoid this, you need to do something such that the signal variation will be minimum. That is, it will not be from 0 to Vm. So to avoid this and to achieve this particular task, what we do is we have connected something which is known as filters. So to achieve this, we have connected some circuit into this, which is called as filter. So we will see how the filter circuits work. And just to give you the clear elaboration because about what I was talking, so you can see, if you see over here, we have implemented a filter circuit, and the variation, you can see the variation has been given by a number delta V over here. So in our previous case, you can see that the variation was from 0 to Vm, but now when you apply the filter circuit, not from 0 to Vm, it is delta V, and how this is achieved and how it will improve the ripple factor, that study we will do at 12.